When a balanced electric motor is turned on, its two bodies, the armature and the stator, rotate in opposite directions. Without external applied forces, the center of mass of the system does not accelerate. Since the centers of mass of the two bodies coincide with the center of mass of the system, the two bodies rotate around their own centers of mass and the center of mass of the system. If an arm is attached to the armature center shaft, the center of mass of the system is located intermediary, in the line passing through the centers of mass of the motor and the arm. In the absence of external forces, the centers of mass of the motor and the arm will rotate in circular paths around the stationary center of mass of the system. The moving centers of mass of the two bodies tend to follow a straight line, tangent to the circles, according to Newton's first law. Due to symmetric opposition, the bodies resist, manifesting inertial resistance to the bending of their paths, as centripetal forces. The net force on the center of mass of the system remains null. This is a classical oscillatory motion of an unbalanced system when free of constraints. Let's consider an unbalanced system consisting of a disk and a rotatable arm, whose proximal end is attached to the center of the disk, which becomes the interconnection between the two bodies. A pair of rebound springs is fixed to the disk, limiting the rotation of the center of mass of the arm around the center of mass of the disk, located at its geometric center. Starting from the moment the spring on the right is compressed by the arm, it applies a pair of equal and opposite forces on the two bodies. Due to its short expansion time interval, the expanding spring applies equal and opposite impulses on the two bodies, represented by the opposite vectors. In this arrangement, the impulses do not act on the centers of mass of the arm and the disk, but at a distance from them. It is well known that when a force is applied on a body, at a distance from its center of mass, the body starts moving in a general plane motion, comprising a translation of the center of mass and a rotation of the body around its center of mass. These motions are impeded by the interconnection of the two bodies, as described in other videos of this channel. Their centers of mass will move around the center of mass of the system. Since the tendencies of the bodies to move in straight paths are opposed, their inertial resistances to bending the paths act on each other, causing their paths to be circular centered on the center of mass of the system. Let's now move the center of mass of the disk to a distance from the interconnection, making the disk a semicircular body. When the arm is attached to the interconnection, forming a two-body system with the semicircular body, the center of mass of the system can be located in the line passing through the centers of mass of the two bodies. The rotation of the bodies remains limited by the rebound springs. Recalling the previous examples, it could be expected that, under the action of the pair of equal and opposite impulses applied by the compressed and expanding spring, the centers of mass of the bodies would rotate in circles around the center of mass of the system. Since the present system is asymmetric, the circular rotation of the centers of mass of the bodies around the stationary center of mass of the system is impossible. The vectors acting on the centers of mass of the bodies must be parallel to the impulse vectors produced by the spring. The center of rotation must be the interconnection of the bodies. The interaction between the bodies under the action of the equal and opposite spring impulses produces the corresponding vectors on the interconnection, detailed in other videos of this channel. If the resultant of the composition of forces on the interconnection is null, the interconnection becomes an instantaneous center of zero acceleration. In this case, the centers of mass of the bodies will move in circular paths around the interconnection. However, when the bodies start rotating, due to Newton's first law, they tend to move not in the circular paths but in straight paths tangent. Due to asymmetry, an inertial confrontation occurs. The semicircular body pulls the center of mass of the arm backward, forcing its path to become a curve between the circular and the straight line tangent. The center of mass of the arm resists this bending and pulls the center of mass of the semicircular body forward, Along its rotation around the interconnection, the arm transfers kinetic energy to the semicircular body, causing its motion forward, changing the position of the center of mass of the system. The arguments concerning this energy transfer is also described with vectors in another video.